Welcome back for the second day in a row. Yesterday I was just able to give you a very quick glimpse into our next topic, which will be very short and sweet, I hope, and that is working with recursive relations. Tried to give you an idea of the fact you've already seen some recursive relations, and our really big goal is to be able to be given a recursive relation and then be able to solve it. By solve it, we mean get a closed-end form, get an explicit formula, get a general formula. There are various ways to say that. We also play around with a little bit of, or a few problems that you have to maybe identify a situation through some investigations that could lead to a recursive understanding of the problem. Then from that recursive understanding, you could hopefully get to a closed-end form understanding of the problem. Before we get too far into it, though, there is some vocabulary. And as I did mention, I'm expecting you to maybe read and study some of the content in the first three sections of section B, and then eventually we'll get to that fourth section. So recursive relations, lots of vocabulary. So here we go. To start, we have what we can call a first-degree linear recursive relation. The degree has to do with how many terms we're dealing with. So a first degree is only going to be working with a previous term. Doesn't have to be the one directly in front of it, but only one previous term. To make it linear, what we have to have is what we're multiplying by that degree, so to speak, term, has to just be some type of a constant. And then we could also either add a function to this whole relation. From first degree linear, we could break it down into two different types, homogeneous and inhomogeneous. The homogeneous, basically we're not having this extra term. It's not a function. There is nothing there. And then that coefficient is just some r. It could be a 1, but it's just some r. Inhomogeneous is where this is also a number. Okay, so this could be some type of a function. And again, we do want to have at least coefficient here. So not so important, but you might see some of these words, so don't let it confuse you too much. We could have a second degree, and the biggest difference is, of course, that we have two terms that affect a new term. And again, two previous terms. The a and the b here are just some type of coefficients. The reason they're linear is they're going to be constants. We could get further into this where the coefficients are functions themselves, but again, that's way, way, way beyond what we want to do here in this course. Eventually, I'll point to some of these problems that you might want to try. So let's just get into some of the things that we're asked to do in this, the first three sections. And a lot of it is just kind of a trial and error and recognition of patterns, playing around with things. Ultimately, in many of them, you're asked to prove by principle of mathematical induction the conjecture. To make sure it holds true. I'm not going to require that. I think you might want to do one or two of these just to practice and review the proof by mathematical induction. So here we go. Here is a recursive relation. We could maybe classify it. It's definitely a linear or first degree. It is linear. This is a function. So it's going to be one of these inhomogeneous. So let's just get to trying to figure out what happens here. The instructions, which I didn't write out, would be basically conjecture a closed form and use principle of mathematical induction maybe to prove it. I'm not going to do the proof part, but I will try to come up with a pattern. So best thing to go about this is just to realize that if this is my given information, it is specific because I know where it starts. I can just get some of the other terms. So this would be the term before it, which is 0 plus 1, which is 1. If I go to the second one, it's going to be the term before it, which is 1, plus the actual n, which is 2, so that's 3. Then I can go to the third term. It's going to be the term before it, which is 3, plus the n, which is 3, gives me 6. And then I could continue this. Term before it, which is 6, plus that term, which is 4. We get to 10. And that will continue. So basically, my series or sequence is 0, 1, 3, 6, 10, dot, dot, dot. As far as the conjecture, this is where it gets a little tricky. You have to kind of pull out all the stops. We know when we see powers of 2 or powers of 3 or products, maybe even factorial numbers. These look close, but not quite. But one thing we maybe would notice with this one is that we keep going up 1, up 2, up 3, up 4 as far as adding. And whenever we see that, it's going to be basically the sum of an arithmetic sequence. So this conjecture for me would be that we get the nth term is simply going to be n times n plus 1 all over 2. And you might remember that kind of as the sum of the first so many numbers of a sequence. However, you could try that very quickly. When n is 0 or 1, it's going to be 1 times 2 over 2. That's good. When it happens to be 4, we get 4 times 5 over 2. So this is just a very common pattern that we tend to see. I could prove this by mathematical induction, but as I said, that's not really what I want to do here. This next one, it's definitely linear because first degree, I keep saying that. It is also linear because that's coefficient's just a constant. This is also a function. Okay, so that creates a little bit of an issue here, but let's see what happens. The first term we already know is 2, so I'm going to write it. The second term is going to be 2 times the term before it, which would be 4, or 2 times 2, plus 2 to the n power. And if we look at that, that's going to be 8. We then go to the third term. It's going to be 2 times the term before it, which is 8, plus 2 to the third, which happens to be, that's 8, 16 is at 24. The next term, it's going to be 2 times the one before it, plus 2 to the 4th power. And that's going to be another number. So 2 to the 4th is 16, 48, that's 64. And I could continue this. So I have this sequence. And I'm supposed to come up with a conjecture for what the closed form is. Well, again, this might bring you back to how we started this course almost 2 years ago, a year and a half ago. Some patterns are very easy to see, this one not so much. One of the things we did try to do, though, was not just look at the end result, because that is challenging. Okay, what I'm going to do is focus more on how did I get that result. Maybe there's some hints that would help me. And I don't know, if I take one of these, for example, this one, this happens to be 2 to the third. So I could break that one down as 2 times 2 to the third plus 2 to the third equals 24. Okay, let's see how that goes. Let's break down this next one. That would be 2 times 2 to the third times 2 plus 2 to the fourth. Maybe that helps. I might even be able to notice that that's going to be 2 squared. Or maybe this. That could be written as 2 times 2 to the fourth plus 2 to the fourth. So here's one of them when n is 3. Here's another one when n is 4. Okay, this can be even rewritten. I could write that as 3 times 2 to the third. Here I can rewrite this as 3 times 2 to the fourth. I think I missed one somewhere. That's going to be 2 to the third times 3. That was my mistake. It's going to be 2 times 2 to the third times 3. So it'd be 3 times 2 to the fourth. So we have that. Sorry about that. So we expand, we find all the terms by using this recursive relation. Just looking at the solutions could be rather challenging. But the clue in getting the closed form is how did you get each of those individual terms? And even within each of these individual terms, you start to see a pattern. So I tried to make them maybe a little bit more obvious here. And then eventually I get to this. Now I'm hoping that you would see or believe that the nth term is going to be the n times 2 to the n. Okay, so just giving you some ideas on how to maybe work through this. Of course, the solutions are in the back of the text, so here's where we stand so far. These first 3 sections, there's just a lot of vocabulary and a lot of information. And I really don't want to overdo it with these types of problems because they can be a little hit and miss as to whether or not you can get that closed form. I do believe that once you have that closed form, you would be very comfortable getting or showing it by proof of or a proof through mathematical induction. However, these are just a few scattered problems through the first 3 sections. The other thing I would really encourage you to read and study. You don't have to complete these investigations, but I think they're rather interesting. One is a Tower, Illinois, and there are other situations that lead to a recursive solution. Investigations on pages 30 to 31 are rather interesting to read, numbers 1, 2, and 3. So I'm trying to separate this recursive relation lesson or topic really into 2 parts. These, which we don't really seem to have any specific method for finding the solution. We just have to come up with a pattern and hope that we can find our solution. And then maybe tomorrow or Friday, we will go over a very specific type, one that we have a specific method on how to solve those types. And we'll take care of that, and then after that, I'll have some type of a collection of problems I'll post and you'll practice. So I think you'll at least have an introduction to these recursive relations. I will say for future reference, anyone studying a computer science type of course, or if you have already, recursive relations will be a big deal. And it will be just that you'll have to study a problem, you'll have to answer it recursively, but then the big question is, can you find it explicitly, or can you find the closed form? So, the design is just to give you an introduction. Good luck working with some of these problems. As I said, if I have things ready by tomorrow, I may even post the next quick little lesson. That way you have it all behind you and you can just work for the next several days. By the end of the week, I'll at least try to post a quick little worksheet for you to practice, get some feedback, and then we'll be 1 week closer to the end. So enjoy your day, and thank you.